Okay, so I give this talk on behalf of the Polar and Polar 2 collaboration. It's a bit of a different subject because we go to Gammaray polarimetry. That was a bit about X-ray polarimetry yesterday, so I can build a bit on that. But overall, the techniques are quite different, and the science case is a bit different. Unfortunately, I only have 10 minutes, so I cannot go into the detail of everything. But with Polar and Polar 2 in the future, the main science goal is to probe the emission, the prompt emission of gamma ray bursts using gamma ray polarimetry. So whereas with optical, there's been much learned about the afterglow, with the polarization of the prompt, we hope to see the emission processes at play and the potential magnetic fields within the jet that are responsible for the gamma ray emission. So as I said, I don't have time to go into detail on exactly what we can learn from this, but simply said, synchrotron emission in this jet would typically result in high levels of polarization depending on the magnetic field configuration, whereas more thermal photospheric emission would result in low levels of polarization. An overview is found in a relatively old paper now by Kenji Toma, but still quite relevant. And for more detailed papers are coming out relatively frequently, so I list two here that came out in the last few years, which go a bit more into energy dependence and the viewing angle dependence, which are all important. So the fact that you can learn a lot from the polarization of the gamma ray component means that it has been attempted quite a few times in the past. Unfortunately, it requires very specific instrumentation. So the first attempts that were made were being done with instruments that were actually spectrometers that happened to be able to do some polarization, but were not calibrated on ground for doing this. Now, on top of that, we don't have any standard candles or calibration sources in the sky. So we cannot do the calibration once we're in orbit, which means you're very susceptible to systematic errors. And on top of that, the measurement is very complicated. So it's very easy to get a wrong result. And unfortunately, this was found in most of these early measurements from the last 20 years. This changed about 1 decade ago from GAP, which was a small dedicated gamma ray burst polarimeter from Japan. It was very small, but it still managed to do some polarization measurements. I list them here in the top. The error bars are still quite large. You cannot really say anything about the results, but the important thing for us was that they showed that these measurements are in fact possible. They're challenging, but possible. So based on this success, we started to do Polar. And I should first maybe explain a little bit about how we measure and why it is so difficult. And so the idea for gamma ray polarimetry is that the gamma ray comes into your detector, and then you let it Compton scatter in your detector, and you measure the secondary interaction of this gamma ray. So you have to measure each gamma ray twice, and then based on the Compton scattering angle, this has a dependency on the polarization vector of the incoming photon. So you have to deduce the polarization of the incoming photon from the Compton scattering angle. Now this is doable. And if you have an unpolarized flux and you measure this Compton scattering angle for a lot of incoming gamma rays, you will get a flat distribution shown here. If it's polarized, you start to get this 180-degree modulation, similar as was shown for X-rays yesterday. But in reality, it's a lot more complicated because you have instrumental effects and issues like that. One of the other issues is that the efficiency is typically very low. Like for a spectrometer for gamma rays, you use all the photons because you just let them interact in your instrument. In our case, we have to throw away about 90% of all the events because these are photons that either don't Compton scatter or Compton scatter too many times. So you need a really large instrument to be able to do these kind of measurements. And the whole thing gets even worse for gamma ray bursts because we don't know where they're going to happen. The prompt emission only lasts a few seconds. So we have to observe the full sky, or half the sky in our case, which reduces your signal to noise. Now, despite all of these setbacks, we still try this using this detector that you see here in the top right called Polar. It's about 30 by 30 centimeters, quite a high effective area for a gamma ray detector, and we observe half the sky with it. This detector was launched in 2016 as part of the Chang'e-2, the second Chinese space lab. It started taking data for about half a year. And during that half year, we detected 55 gamma ray bursts along with 2 pulsars, which will be discussed in the upcoming talk. But now let's focus on the gamma ray bursts that we saw. So out of the 55 that we saw, most of them are too weak to actually do anything for polarization, or they were too far off axis, or other issues, but 14 of them were good enough to do some kind of constraining measurements. Now, constraining in gamma ray burst means error bars of 10, 20 degrees, which is already very good for us. And in fact, with Polar, we were able to do some of the most constraining measurements for 5 of 6 of these gamma ray bursts. So here on the left, you see the posterior distribution for the polarization degree for these 14 GRBs. Some of them, the distribution is still quite wide, but some of them also you see that basically we can exclude everything above 30, 40%. And our full sample is completely compatible with either a low depolarized flux, meaning 10, 20% at most, or an unpolarized flux. So this matches actually with most of the emission models. So on the top right, I'm showing a plot that is by Ramandeep Gill that will be published soon, but I was already allowed to show it. So here you see the polar measurements results in brown and the predictions from 3 different models, synchrotron models with different magnetic field configurations. So with polar, it seems we can exclude the toroidal magnetic fields, but even that is tricky. And we're compatible with all the other kind of models. So in that respect, we haven't learned much from the polar results. And on top of that, there's another complication, because what I show here are the time integrated polarization measurements. Now, for some of the GRBs, 2 in particular, we were able to slice them up in different time slices. And then here we show the polarization degree along the radial axis and the polarization angle along the polar axis for the different time bins of one of these single pulse GRBs. Now, this is a single pulse GRB, which means that we expect all the emission to come from one specific emission region. So it's a very nice probe. And what it looks like is that the polarization degree is actually quite high, but the polarization angle seems to change very rapidly during the GRB. Now, this could explain why overall for most of the GRBs, we don't see any polarization degree. It would simply be because in time integrated, the polarization angle changes too rapidly. And what you get is a washed out polarization, and it looks like 0, but in fact, it is actually maybe 30, 40%. Now, unfortunately, we can only find hints of this. So we find the same effect for 2 of the GRBs where we have a single pulse. We didn't have any other of these kind of GRBs. And for these 2, we can sort of say with 90, 99% confidence level that we see this change, but it's not fully constraining yet. So really to probe this, we need more time bins, more precision. And unfortunately, with the polar data, we cannot do this kind of things because we simply don't have the statistics. So this brought us to the idea to come up with Polar 2. Quite rapidly after finishing our analysis, we came up with the idea for building a bigger instrument. We kept the same collaboration from the University of Geneva in Switzerland, IHAP in China, NCBJ in Poland, and MPE in Germany to develop this instrument. And it was quite popular, so we actually managed to get it approved for launch rather quickly. So this will be launched in 3 years from now to the China Space Station in 2024. More details you can find on the website that I link here. But basically, this detector will be significantly more sensitive. Firstly, by just making it 4 times bigger than Polar. But secondly, by improving the technology, because we learned a lot by building Polar and we found a lot of the shortcomings of it. And by improving the technology, we get an extra factor 2 or 3 in sensitivity. So in total, the thing will be an order of magnitude more sensitive. This means that since gamma ray burst polarimeters are already so, you need a very big sensitivity. So Polar was already quite sensitive, but this one will be probably the most sensitive detector in orbit at the time in gamma rays, which means GRBs like 1708717A, which was discussed in the previous talk, with Polar, this will be very easy to spot. It will be much more sensitive than the Fermi GBM detector that spotted this one. So on top of that, we can do very good gamma ray burst polarimetry of this one. We will also be very sensitive. And thanks to the computing power of the China Space Station, we will be able to send real-time alerts to ground very quickly. So within a few seconds for even the weakest GRBs that we observe. So we will observe half the sky. So that brings me to the outlook. So we did Polar. It was a success, but unfortunately, but the main thing we learned from the results was that it simply wasn't sensitive. We need to have more statistics and more GRBs. So we started building Polar 2. We're now building it these days. So on the top, you see some pictures of the developments. On the right, you see the kind of sensitivity that we gain with Polar 2. So this is measured in the minimal detectable polarization, which is basically showing that for a gamma burst like 170817A, we can not really do any polarization. But if it's 2 or 3 times brighter than that, we will be able to at least say if it was very highly polarized or unpolarized. Whereas if we get significant, like 10 times more sensitive gamma ray bursts, we start to be able to do measurements similar to the best ones that we did with Polar. And for normal GRBs like Polar, we were able to measure polarization levels as low as a few percent. So apart from that, providing at least 50 gamma ray burst detailed measurements per year, we will also be able to provide on-ground reports of kilonova events or gravitational wave events very quickly to the community, which hopefully also helps other people. That's it from my side. Thank you very much.